Continuing with Chapter 8, Personal Finance. We looked at simple interest, and now we're going to review compound interest. The objectives are to use compound interest formulas, calculate present value, and understand and compute effective annual yield. So first of all, what is the difference between simple and compound interest? Simple interest was computed only on the principal. Compound interest is interest that is computed on the original principal as well as any accumulated interest. So the interest is on the interest. To calculate the compound interest paid once a year, we're going to use a formula that's similar to what we had, but it's a little more complicated. It's A is equal to P times the quantity 1 plus R raised to the T power, where A is the account's future value, P, the principal, is its present value, R is a rate, and T is a time in years, or number of years. So the variables mean the same, the formula is just a little different. We're going to look at some examples. You deposit $2,000 in a savings account at a hometown bank, which has a rate of 6%. We want to find the amount of money A in the account after 3 years subject to compound interest and find the interest. This is similar to one of the examples we had in the previous section, only it was on simple interest. So first of all, the principal P is $2,000. That's how much you're putting into the savings account. The interest rate is 6%, which translates to 0.06, and the time is T, 3 years. So we're going to substitute those values into our interest formula. The important thing to remember here is you always work inside the parentheses first. So again, we're going to do the 1 plus 0.6, or 0.06, sorry, I got my point in the wrong place. So we do that first. That would be 1.06. This time the time is outside of the parentheses as an exponent. So we are going to take the third power of 1.06 because the parentheses tell us that the third power only applies to the part inside the parentheses. So we take 1.06 raised to the third power and then take that times 2,000, which gives us this result of $2,382.03. So that is repeated on this slide. The amount in the account after 3 years is $2,382.03. We take the difference between this amount and the principal to obtain the interest. So $2,382.03 minus your $2,000 that you started with indicates that the interest for the 3 years is $382.03. If you deposit P dollars at rate R in decimal form, subject to compound interest paid n times a year, then the amount of money A in the account after T years is given by this formula, which again is a little different from the one that we just had previously. The thing with these problems is be sure that you select the proper formula. Again, A is the account's future value and principal P is its present value. So with this example, we deposited $7,500 in a savings account that has a rate of 6%. The interest is compounded monthly, which is different from what we had before. How much money will you have after 5 years? And find the interest after 5 years. So our principal P is $7,500. The interest rate is 6%, or 0.06. The time is 5, and N is 12 because we're compounding monthly. So you've got another variable in this expression. Substituting this into the compound interest formula down here, we end up with 7,500, which is P. We've got 1 plus the rate 0.06 over 12, which is N because we're compounding monthly. This is all inside the parentheses. NT is going to be the exponent that we're raising, but is inside the parentheses 2. So we have N is 12, T is 5, that gives us 60. So again, we start with what is inside the parentheses. We would divide 0.06 by 12 and add 1. You can see over on the next one, once we add the 1, we get 1.005. This is raised to the 60th power. Only the part inside the parentheses is raised to the 60th power. You can do this on your calculator. 1.005 raised to the 60th power, then times your 7,500 gives you approximately, that's what the wavy lines mean, $10,116.38, which is repeated on this slide. The amount in the account after 5 years is $10,116.38. But we want to find the interest, so we're going to subtract what we started with, the 7,500, and we can, which tells us that the interest that we received for the 5 years compounding monthly is $2,616.38. Now this is compounding interest at a specific number of times. On the next slide, we're going to look at continuous compounding. Some banks do use continuous compounding where the compounding periods increase indefinitely. This is yet another formula. After T years of balance A in an account with principal P, remember the A, the P, the T still stand for the same thing, and the annual interest rate R in decimal form is given by these formulas. For N compounding periods per year, we had the formula that we just used in the previous example. For continuous compounding, we have A is equal to P times E to the RT, or excuse me, NT. And the NT is the power just of the E. Here's example 3. You decide to invest $8,000 for 6 years, and you have a choice between 2 accounts. The first one pays $7,000 per year compounded monthly. The second pays a little bit lower interest rate per year, but is compounded continuously. You want to determine which is the better investment. So the better investment would be the one that gives you the larger balance at the end of 6 years. We're first going to use the 7% instance. So we're going to use the formula A is equal to P times 1 plus R divided by N raised to the NT. And working this out, remember that we solve inside the parentheses first. We divide the rate by N, which is the number of times it's compounded. And then when we get this, we add the 1. We're going to raise this to the 12 times 6 value or exponent. Multiply by 8,000, and this is approximately $12,160.84. So this would be the balance in the account after 6 years for the first option that we have. Now we're going to look at the second option, which is a lower interest rate, so you might think that that would give you less money. We use this other formula this time. We use the E, which you can find on your scientific calculator. If you've got a cell phone, it will have a calculator, and if you turn the phone to landscape, it's going to give you a scientific calculator, which will have all of these options that you need to include working with E. So when we do this, we're taking E to the 0.0685, that's the rate, times 6. Our number or coefficient in front of the E is 8,000. So working this out on our calculator, we're going to get $12,066.60. So the better investment for this particular example, looking back at the number we got for the previous one, would be the 7% monthly. Now we have calculating present value. I think I skipped a slide. Let me go back. Here we go. Okay, if A dollars are to be accumulated in T years, like you have a plan that you want a certain amount of money in an account that pays a rate of R compounded n times per year, then the present value P that needs to be invested is given by this. So in other words, you have a goal, you want to have a certain amount of money at the end of a certain time, and this will give you that value that you have to invest in order to reach your goal. And here's an example. How much money should be deposited in an account today that earns 6% compounded monthly so that it will accumulate to $20,000 in 5 years? So your goal is $20,000. We're going to use the present value formula. A is 20,000. That goes in the numerator. R is, once we convert to decimal, 0.06, N is 12, and T is 5. So when we solve this, we're going to, we already know that we've got 20,000 for the numerator. We're going to work on the bottom part this time, but you still do inside the parentheses first, divide the rate by n, add the 1, then take that to the n times t, which 12 times 5 would be 60. So when you do all that, you're going to get a number for your denominator, which you will divide into the numerator, which is the 20,000, and that gives you $14,827.4439, which we know we have to round to 45. So this tells us that to reach $20,000 under the circumstances that we're given, we're going to have to invest $14,827.45 today. Next, effective annual yield. The effective annual yield, or the effective rate, is the simple interest rate that produces the same amount of money in an account at the end of 1 year as when the account is subjected to compound interest at a stated rate. And that's what we're going to look at in this final example for this section. You deposit $4,000 in an account that pays 8% interest compounded monthly. You want to find the future value after 1 year. You want to use the future value formula for simple interest to determine the effective annual yield. So first, find the future value after 1 year. We're going to use the compound interest formula like we did at the beginning of this section. A is equal to P times 1 plus R divided by N raised to the NT. And when we do this, working inside parentheses first, then taking the power, and then finally multiplying by 4,000, we get approximately $4,332. The effective annual yield is the simple interest rate. So we would use the future value formula for simple interest to determine the rate. So that means we're going to use A is equal to P times 1 plus RT. Our future value is $4,332. Our P principal is 4,000. What we're trying to find is the rate, R. This is the instance where we take the 4,000 outside the parenthesis times each term inside the parentheses. So it'd be 4,000 plus 4,000 R. We have R on one side and the numbers on the other side. When we subtract 4,000 from both sides, that gives us 4,000 R is equal to 332. And then dividing by the 4,000, which is the coefficient of R, we get 0.083, which we write as a percent, 8.3%. We have covered a lot in this section. You may want to go back over this video again, and I would recommend that you read this section in the book and work through all of the examples.